Hey everyone, welcome to the third video for section 3.5. So in this video, we're going to go over real quickly when this method can fail, or when guessing the solution directly can fail, and so what do you have to do to modify that to get something that still works. So we'll look at that, and then we'll look into a couple examples of using this method to find solutions to equations. Let's go ahead and jump right on into it. So the first point for this video is when can guessing that solution fail? Now the main way this can fail is if the guess we make solves the homogeneous equation. If this happens, then when we plug in y of t to the left-hand side, we're just going to get 0. We're not going to get something we can match up to g of t. We're just going to get 0. And that's bad. So how can we fix this? Well, one way to fix it, and turns out the easiest way to fix it in the way that you end up doing pretty much every time, is you just multiply by t. It's sort of the same idea as we had for doing reduction of order to get the next solution for a repeated root case. It's a little bit different, but the idea is kind of similar. The idea is something like this. If I take the function t times y of t and plug that into my equation, when I take derivatives of this, I'm either going to get derivatives of y all times t, and those will all go to 0 because I knew that L of y was 0. So if I hit all derivatives falling on y, I will get t times L of y, and that's going to go to 0, so we're fine. But when the derivatives fall on t, I get the function y of t showing up in different quantities, which means I'm going to get different sort of ratios on how the different terms come up, which means in this case I might be able to solve the equation here. So this ends up being a good guess for that problem. And basically the idea for these are multiply by t. If that doesn't be enough, try multiplying by t squared, then by t cubed. Just keep adding powers of t until you get something that works. And if you're able to guess a reasonable form for the solution based on the right hand side, then multiplying by t eventually will get you an answer. For second order equations, you don't need to go more than once or twice. But you don't have to go more than once for second order equations. But for higher order equations, you may have to go 2 or 3 times or something like that. But your guess ends up being you want to guess t times y of t, and we'll see an example at the end. The second example here in this section is going to be one where the y of t fails, so you guess ty of t and then it works. So this is the main way that if you could guess something, that it's going to fail. So that's something to just keep in mind for doing these problems. So let's go ahead and take a look at an example of solving a problem using this method. So I want to find a particular solution to this ODE. Y double prime plus 3y prime plus y equals sine of 2t plus t squared plus 1. Now this term particular solution is used to describe this capital Y that we're getting from this method that solves our non-homogeneous equation. And then we get the general solution by adding that to the homogeneous solution to the equation. So if this is my right-hand side, sine 2t plus t squared plus 1, what should I guess for my y of t? Well, I should guess y of t equals a sine of 2t plus b cosine of 2t. That comes from the sine of 2t term. And then plus a c2t squared plus c1t plus c0 from the polynomial term. Now I'm guessing a t term as well because I know when I take derivatives of t squared, I'm going to get t's. So I better put a t in there as well to make sure I can cancel everything out at the end. So now what I have to do is I have to take derivatives of this guy and then plug them into my equation. So y prime of t is going to be 2a cosine of 2t minus 2b sine of 2t plus 2c2t plus c1. And y double prime of t is going to be negative 4a sine of 2t minus 4b cosine of 2t plus 2c2 from taking derivatives of the t function. And I want to take all of that and shove it in my equation. So let's do that. So my equation was y double prime plus 3y prime plus y. So I get y double prime plus 3y prime plus y. And what do I want? I want this to equal sine of 2t plus t squared plus 1. Now how we're going to do this is we are going to match up all the terms that have the same function of t attached to them. So I'm going to write that out starting below, and I'll use a notation here that hopefully should make sense. So the first thing I want to do is I want to do an equation for sine of 2t. What equation do I get here? Well, I have a minus 4a from the first term. I have a minus 6b from the other sign term, and then a plus a, and I want this to equal 1, right? So I got the minus 4a from this, I got the minus 6b from 3 times minus 2b, and I got the 1a from this, and I got the 1 from this coefficient here. Now I want to look at cosine of 2t, and this is going to be minus 4b plus 6a plus b equals 0 because there's no cosine on the right-hand side. I'm going to get 3 more equations, a t squared, a t, and I'm going to call a 1, but I mean a constant equation here. And now I'm going to scroll back up again so I can write them all out. My t squared equation is just c2. That's the only t squared term that shows up. I want that to be 1. My t equation is going to be 3, no, it's going to be 6c2 plus c1, and that's got to be 0. My 1 equation is going to be 2c2 plus 3c1 plus c0 equals 1. 2c2 came from the first term, 3c1 from the second, and then a c0 from the third. So now I just have these 5 equations with 5 unknowns that I'm trying to solve. I'll write this one again. This is minus 3a minus 6b. This is 6a minus 3b. This just tells me c2 equals 1. Then this one tells me that c1 is minus 6. And this tells me that, so this is 2, this is minus 18. So that means I need c0 to be 17. So that gives me my c constants. Now I need to solve for my a constants. So what I'm going to do is I'm going to double the first equation and then add them together. I'm going to scroll down a little bit. So if I double the first equation, I get a 2 equals minus 6a minus 12b. 0 equals 6a minus 3b. I can add them together. 2 equals negative 15b. So b equals negative 2 over 15. And if I plug into the second equation, this then tells me that a must equal negative 1 over 15. So then my full solution, when I write it all out, putting all the constants in, tells me that my particular solution, y of t, should be negative 1/15 sine of 2t minus 2 over 15 cosine of 2t plus t squared minus 6t plus 17. And that solves the non-homogeneous equation. If I wanted to get all solutions to the non-homogeneous equation, I would then add a solution to the homogeneous equation, c1y1 plus c2y2. And if you plug that back in, you'll see that this actually does solve the non-homogeneous equation. All right, so there is a basic example of how to do these sorts of problems. Yes, they're a little long. Sometimes the numbers are a little nasty, but it comes out not too bad in the end. Now our second example here is going to be one of the ones where it doesn't work because of the homogeneous problem. So let's look at trying to solve y double prime minus y equals 2e to the t. So our right-hand side looks like e to the t, so we should guess y of t equals a times e to the t. But if we plug it into the left-hand side, what we see is y prime is a to the t, y double prime is a e to the t. So the left-hand side just becomes a e to the t minus a e to the t equals 0. And that happened because e to the t solves the homogeneous problem. You should be able to prove that's what happens. You can find those solutions. They're e to the t and e to the minus t. So instead, what do we guess? We guess y of t is going to be t e to the t. Then y prime of t is going to be e to the t plus t e to the t. And y double prime of t is going to be e to the t plus e to the t plus t e to the t is going to be 2 e to the t plus t e to the t. And now we plug in. So I want y double prime minus y is going to be 2e to the t plus t e to the t minus t e to the t. And I want that to equal 2e to the t. Okay, we got lucky here. And let me make sure to point this out. I should have put an a in front of this, which means I get an a here and an a here, a here, a here, a here, an a in front of that, and an a there. So this is a, and a. These two terms still cancel, and this means I need 2a e to the t equals 2e to the t. So I want a to be 1. So my y of t that I should get is just t times e to the t. That was a little sloppily done, but that's a point to make sure. Even if you do the t, you still have to put the constant in there to make sure that it still works out. All right, so there's two examples for this video. One that actually shows you how you use this method to solve equations. Another which shows you that if it doesn't work, all you really want to do is multiply by t to give you a different guess, and that can still work out just fine. Because what happened here, basically I ended up with an extra 2 flying around here from these derivatives stacking up on each other. And that's going to change how terms cancel out, which means you aren't going to get rid of everything when you do this sort of cancellation, when you do the subtraction. Alright, so that's it for this video. Thanks a lot for watching. In the next section, we'll tackle a different method for solving these called the variation of parameters. Thanks for watching, and I'll see you then.